Yes, guys. Are you able to see the screen? Right. In our previous class, we already covered the voltmeter. Now today's class, we will going to cover the ammeter. Now, uh, what is a voltmeter? We already covered it, right? See this slide. Voltmeter internal structure is in connected in parallel, right? But connected in series, but voltmeter connected in laboratory parallel to the device for measuring the voltages, right? Now, similar way, in if I talk about the ammeter is connected in laboratory in series with a device, right, for measuring the current. Now see this one example, but now see this was one example and try to solve it. If I use a 0 to 1 milliampere linear instrument with an internal resistance of 100 ohm is to be converted into the 0 to 10 ampere ammeter. Means you want to convert this 0 to 1 milliampere ammeter into the 0 to 10 ampere ammeter. So how to convert it, right? So, as we see, the voltmeter internal structure is connected in series, right? Similar way, if I talk about the internal structure of ammeter, is nothing but the a parallel resistance connected with a resistance connected in parallel with the meter resistance. Okay, and this meter is connected in series with your devices. For example, see here, this is your structure, right? This is your emitter, and here your, this is your source. Okay, this is your source, and this is your load. This is your load. Now you want to measure the current flowing through this your load, right, consuming by this load. So for that you need to connect the emitter in series with this. Now emitter connected in series with this, what it means, as you know that internal resistance of for ideal emitter internal resistance of emitter is 0, right? Similar way, if I talk about the current source, ideal, for current source, ideal current source, what is the internal resistance of current source is infinite, right? That's why current source is connected in parallel with any load. And if I talk about the emitter connected in series with this. Now, see the internal structure of emitter. See, internal structure. Uh, if I see here, internal structure of this emitter is nothing but the a small resistance is connected with your meter resistance. Okay, so this is your meter resistance, and this is the RSH which is connected in parallel with your meter resistance. Now, if I observe that this value of RSH is very very small, that's why the majority of current is flow from this here shunt resistance. Okay, and because of this resistance is very low, a very small amount of current is flowing from this meter. And the meter is all, any meter is work only the that principle which I already discussed. First, entering current is converted into the force, and force is converted into the force is a responsible for your deflection, right? And deflection angle of theta, and this theta, because of the theta your pointer gets moved, right? And by using the calibration process, you are easily find out the uh, required quantity, right? So here our aim to find out the current, and find out the current, or you can say to increase the limit of your emitter from 0 to 1 ampere to 0 to 100 ampere. So this is a basic structure of your ammeter, which is meter resistance is connected with your shunt resistance, and this is whole meter is connected in series with your load. Okay. Now now how to convert this, how to convert this 0 to 1 ampere to 0 to 10 ampere ammeter. So this structure is already present with this, right? 0 to 1 ampere. Now things is that you need to find out the value of this RSH. Okay, for 0 to 1 ampere. Once you find out this value of RSS and RM, then for the second case, you need to add this extra uh, resistance with this, or the combination of with this. If you add that resistance, then you are able to increase the rating of your emitter. Now see here, apply simple KVL KCL here. This is your total I is flowing from this side. Okay, wait. So this is your structure which is already present with you, right? 0 to 1 ampere, and some resistance are there for this meter. You want to increase that emitter reading, right? So one extra resistance is connected in shunt with this meter, and this is your uh, supply side. It means I ampere is flowing from this side. This is your RSH, and this is ISH, current flowing from this side, and this is your IM, meter current. Okay. Now if I talk about this, both are connected in parallel. If I am flowing from this side, right, for this branch, so what is the voltage drop for this branch is Vm. I take here Vm. Okay. So if I take Vm here, so this is your positive and this is your negative. Vm is nothing but your Im into Rm, and both are connected in parallel, so I can say that the ratio of these two are equal. So here see, I is nothing but your RSH plus Im. Okay, this is a KCL, and this is both are connected in parallel, so I can say that the this Vm is equal to for this VSH, right? So this is your ISHS into RSH is equal to Im into Rm. Okay, this point is clear to all, right? If you have any doubt at any point, please ask. Okay. Now, now see here. What is the value of this Rm? This Rm, according to your question, Rm is given to you is 100 ohm. Okay. So this is nothing but your 100 ohm. Now, what is a maximum current from Im for this 0 to 1 ampere is I maximum value of this Im is 1 milliampere. So this is in milliampere. Okay, according to your question, this is your milliampere, right? So Im value is 1 milliampere. Now what you want to measure the current from your source side is you want to convert that emitter into 0 to 0 to 10 ampere. So I consider here this I value is you want to convert into 10 ampere. Okay, so put that value in this. Now one more thing. Now see how to find out this RSH. So ISH, sorry, how to find out this Im by using this. So I am is nothing but your I into RSH. Okay, RSH plus 100. Now see what happening here. This is your IM, right? And I simply apply the this KVL here. This is your RSHS. Okay, if I apply KVL here, so see, this is your IM, 1 milliampere into 100 ohm. So this IM, this I simply write here IM 1 ampere, 1 milliampere is decode with you, uh, represent with this IM. Okay, I'm not decode this IM here. Now, uh, okay, so this drop is equal to this drop, ISH, and this ISHS is uh, okay. This ISHS is represent with this I 10 with this I total I. Okay, so what is a total I is parallel combination of these two. Okay, guys, wait a minute. Yes, guys. So this is with you. So put the value of this IM. IM is nothing but your 1 milliampere. I value you want is that is 10 ampere, and you need to find out this RSH, which you are connecting with this parallel with your meter. Okay, so RSH plus 100. Now when you solve it, you will able to find this RSH with 0.01 ohm. 0.01 ohm. Now if I put this RSH 0.01 ohm, so this is very small resistance, right? So majority of current is bypass from this branch only, and only a small or maximum current flowing from this from your meter is only for your maximum full load scale of your reading, which is nothing but in this 1 milliampere. Okay, because you design the meter only for the IFSD, means full u IFSD, full scale deflection current. Okay, any meter you are going to design that work only for this full load, uh, full scale deflection current only, because you can't design the meter, you can't use that meter which is allowed to flow 10 up to the 10 ampere current from within, it means from it. Okay, because the any meter there also internal resistance. If that high amount of current flowing from that side, from this side, so maximum losses are there. So we design the meter such that a very small resistance is connected in parallel with your meter, so majority of current is passed from this shunt ohm resistance. and a small amount, or you can say IFSD current flowing from your meter side. Okay. Now the same way, you can also increase the uh, range of your emitter from uh, this is for 0 to 10 ampere, right? If I say that if I want to design the meter from 0 to 20 ampere, if I say if I want to design your meter with 0 to 10 20 ampere, then what you need to do with your meter is same way you want to connect, you need to connect the this shunt ohm resistance, means you need to connect new shunt ohm resistance with your meter, right? So what is the maximum value of current is your this is depend on your meter, right? So your meter is only allow means 1 milliampere current, right? Because you are converting this 1 milliampere to the 0 to 20 ampere for this case. So maximum uh, current allow for your meter is only for only this 1 milliampere only. Okay, so this is same 1 milliampere, which is nothing but your I into RSH divided by RSH plus 100. Okay, I into RSH plus 100. Now, uh, yes, guys. Now, see. So, this is your IM is 1 milliampere, right? 1 milliampere. I you want is 20 ampere. So, find out this RSH. If I solve this, if you solve this, you will get this RSH value. When you solve it, you will get 0.005 ohm. Okay. Now the question is that why this? Okay. See here, why I taking this now? When I see, when I multiply this, simplify this equation with this, which is nothing but your I into RSH. Okay, so this is your new scale of current, right? New reading, and this is your meter, or you can say maximum current that a meter can allow to flow uh, within it, right? Because of, for the safe operating of your meter. Okay, so this is nothing but your RSH plus 100. What is that? This 100 in any now see this is a your equivalent circuit, right? So this is your meter current, so this meter current is nothing but your this I. Okay, so that meter you want to that meter, this is your meter, right? This is your 100 is given to your internal resistance of your meter. So this IM drop of this both are equal to the majority of current flowing from this side. So we can say that the total current is flowing only from this branch, a very small amount of current flowing from this side. So for the meter working condition, we will consider this equation. Okay, I will okay, we will discuss in below. See here, there are more equivalent resistance of this emitter. Now, this is a process. In any rating of a emitter or voltmeter, maximum value of current passing through. Now, see, voltmeter in any rating of emitter and voltmeter, maximum value of current passing through your meter is IFSD. IFSD means full scale deflection current. In emitter is a practical application of KCL. Okay, and voltmeter is a practical application of KVL. This is a comparison of this emitter and voltmeter. Voltmeter inside circuit is connected in series, but the voltmeter used in lab is parallel. Emitter inside circuit used emitter inside parallel circuit used, okay, but in lab emitter used in series. Network equivalent of emitter is such that RSH into is equal to RM. Now see, if I consider I here, okay, if I consider I here, so this RM, I consider I am flowing from this branch. So what is the equivalent current flowing from this side is I minus of I am, right? I minus of I am. Simple KVL I apply here. I apply say KCL, Kirchhoff current law. Okay, so both are connected in parallel. So I use the, this is a common potential, right? Common potential. So this drop is equal to this drop. So what is the current flowing from this side? This branch is I minus of I am multiply by RSH, which is equal to voltage drop from this side is I am multiply into RM, right? Now, if I solve this, I into RSH minus I m into RSH is equal to I m into RM. Now, see, taken this is I m, right? This is also I m. If I common out this I m, what I have RM plus RSH, right? RM plus RSH. Now, if I take the ratio of these two, I by Im is equal to Rm plus RSH divided by RSH. Okay, this is the equation, or you can say Im divided by I, which is equal to RSH divided by Rm plus RSH. Okay, so we use this equation in above. I hope now you are clear from this, from where I use this equation. Okay, this is simple the equivalent circuit of this emitter. I simply apply the KCL in that in this point, and then I take the KVL. Okay, or you can say the common sense both are connected in parallel, so voltage drop of each branch is equal. So I simply equate them and solve this. When I solve this, I will get this. Now see, this is a your meter full scale deflection current, and this is a range from which you want to change, right? And this is a shunt resistance which we required for each time when you change the scale of meter. Now this RM concentrate, this RM is given, is provided with your original meter, right? Which is here. Now see, in this question, what is this RM is nothing but your 100 ohm, right? 100 ohm is given to you. So use that 100 ohm. Okay, so and this is nothing but your, here your RM, and in this I minus of Im. Now use that equation which I discussed in below. Okay, so up to this all of you clear, right? Now this is one question. Now this is one question. uh, in previous class we I already discussed the sensitivity case, right? Now different sensitivity is given to you. Now see that point also. If sensitivity is given to you, sensitivity, what is the formula of this sensitivity is change in output upon change in input, change in input, right? And one more is 1 upon IFSD. If I replace this IFSD with voltage per ohm, right? So ohm is, yeah, going to numerator side. Now see, so sensitivity unit is ohm per volt. If I know the sensitivity, for example, this is 100 kilo ohm. I put this 100, this is ohm, right? So R by V, and V is given to you. So from this you can easily find out the value of R. Okay, in previous class here, if you find out the sensitivity, find out the value of R here. Okay, so by this sensitivity you will get the value of R is 500 ohm. When you find out the value of R with this 100 kilo ohm sensitivity, so you will find out the sensitivity, R value is nothing but your 500 5000 kilo ohm. So this is your R for this. So when you put this 5000 kilo ohm with this and take the parallel combination of this 50 ohm and 500 kilo ohm, 5000 kilo ohm, right? So then only you will get this 49.999. Okay, so from the sensitive itself, you will able to find the resistance. Now in this question, 200 voltmeter with the sensitivity of 10 kilo ohm per volt and 20 kilo ohm per volt respectively are connected in series. Okay, 2 meter is given to you, and both this meter are connected in series. Now what you want to find out, find the maximum value, find the maximum voltages that we can measure with this series combination. So you need to find out the maximum range of the meter that can be measure uh, your voltages, right? If you use this two combination of voltmeter. Now what is the range of first voltmeter is 0 to 100 ohm, 100 volt, right? Second is 0 to 100 ohm volt. Both voltmeter rating are same, but the difference is that sensitivity are different. Now see, if the sensitivity are different, then what is the effect? Sensitivity, if the 1 meter sensitivity is very high, so I can say that sensitivity is very high. See the formula of sensitivity. Sensitivity is nothing but your 1 upon IFSD, right? If I say that sensitivity is very high, then IFSD is very low, then only the your sensitivity is very high, or I can say that R by V. Okay, now the voltage is constant for your meter. Okay, for so I can say that sensitivity is directly proportional to your resistance, right? Now, for any meter is a safe working current is nothing but your nothing but the IFSD, right? Full scale deflection current of that meter. So you need to find out the IFSD for each meter from this combination. If I find out the IFSD, full scale diffraction current, this is the safe operating current for any meter. Okay, so for full scale deflection current for meter 1 is nothing but your 1 upon S. S is nothing but your sensitivity. If I find out this, you will get 1 by 10 kilo ohm per volt, right? So this is nothing but your, if you find out this, you will get zero point 0.1 milliampere. Okay, and what is the value of IFSD2 is nothing but here, this is here 1 upon S1 and this is here 1 upon S2. Put that value of S2 is 20 kilo ohm per volt. if I put this 20 kilo ohm per volt is 1 by 20, that means 0.05, right? 0.05 milliampere. So if these both meter are connected in series, right? So what is a maximum preferable current flowing from that meter is 0.05 only. Why? because अगर 0.5 के ऊपर करंट जाता है, 0.5 के ऊपर करंट जाता है, सो आपका जो मीटर टू है, राइट, सो योर मीटर टू, ठीक, so your meter 2 will be damaged, right? So what is the maximum permissible current flowing from this combination is only up to the 0.05 milliampere. So uh, only point 0.05 milliampere can flow from this combination. Okay, so I can say that this is your combination, right? This is your meter 1 and this is your meter 2. So it has some resistance. So we can't flow above the point 0.5 point 0.05 milliampere. Okay, with your actual circuit for the safe operating condition. So let's say this is your meter one. Okay, meter one M1, and this is your meter two M2. Okay, so S1. What is a S1 for this meter one is S1 is nothing but your 10 kilo ohm per volt. And what is the value of I1? IFSD1. IFSD1 is zero point 0.1 milliampere. Okay. See, I am talking about the internal structure only. Okay. And M2. What is the value of M2? M2 is nothing. What is the IFSD for your M2? IFSD is nothing but your 0.05 milliampere, right? And S2 is nothing but your 20 kilo ohm. 20 kilo ohm. What is so? And the range is 0 to 100 volt, right? And this also 0 to 100 ohm. Now अब बताओ, देखो इसका IFSD इसका 0.05 मिली एम्पियर, राइट? एंड योर current flowing from your circuit is also 0.05 milliampere. So is uh, 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 this meter is measure up to that full scale reading, right? Because the maximum value of IFSD 2 is nothing but here the same, right? Both are same. So I can, if both are same, then this meter is able to measure up to 100 volt, right? And the, now if I talk about this, now compare this actual current flowing is 0.05 milliampere, but what is a full scale deflection current is zero point 0.1 milliampere only. So IFSD, IFSD 1 is, this is your I current. Let's say this is your I am current. Okay, I am current. So IFSD is nothing but your two times of I am current from this. Okay, from this side. If I talk about this side, okay, for meter one. So this is nothing but your two times. So IFSD, what is the value of IM is IFSD 1 divided by 2, right? Which is IM. Now, see, if IFSD 1 is getting half, right? IFSD, IFSD 1 getting half, right? So this is your new IFSD for this meter. Okay, और सिंपल से अगर इसका IFSD करंट हाफ हो गया, राइट? हाफ हो गया ना आईएफएसडी करंट, पहले पॉइंट वन मिली एम्पियर था, अभी कितना हो गया, 0.05 मिली एम्पियर हो गया। सो उसकी रेंज भी हाफ हो जाएंगी, बिकॉज बोथ आर डायरेक्टली प्रोपोर्शनल टू ईच अदर, राइट। वी ऑलरेडी सी द रिलेशन बिटवीन देम, ठीक है। क्योंकि okay, so only the variation happen in this meter is IM. With this IM, no reading is, we are not changing the scale of reading, right? कुछ हम उसमें ना ही एक्स्ट्रा रेजिस्टेंस ऐड कर रहे हैं, ना कुछ कर रहे हैं, उसका रीडिंग भी हमें सिर्फ करंट मेजर करना है। सो आपका अगर आईएफएसडी कम हुआ, सो योर स्केल ऑफ रीडिंग ऑल्सो गेट हाफ। So you only measure with this half of IFSD. You only measure with this IFSD is 50 volt. 100 divided by 2, right? Simple, 100 divided by 2. You are only able to measure 50 volt. Now both are connected in series. So 50 plus 100 is equal to 150. You are able to measure with this combination only up to the 150 volt. Okay, 150 volt. Simple. Use the KVL case. This meter 1, meter 2, and this is your total. Okay, this is your current flowing from this side. So this is plus and this is minus. This is volt, is nothing but your 150 volt. You are only measure with this, with this 2 meter is 150 volt, meter 1, meter 2. Meter 1 gives you up to the reading 50, up to 50 volt, and meter 2 gives you up to the value 100 volt. Okay, so actually this meter, what is the scale of calibration is this is a 0, this is a 50. If I consider this is your 100 volt, so this is a IFSD, right? IFSD at initial IFS, when current is not flowing, this is your IFSD. If IFSD is not going, goes to up to its maximum value, because of the same operating condition of your meter, your IFSD goes only up to the 50 volt, right? Because half of your IFSD. But the same way, when I talk about the meter 2, your full scale deflection current are able to go with this 100 volt. Okay, and this is your 0 port, and this is your 50 volt port, right? So at the because the maximum total maximum current flowing from this meter is 0.05 milliampere. So for meter 2, 0.05 milliampere is your maximum full scale deflection current. So that's why for this meter 2 you can measure up to the voltage 100 volt. Okay, I hope this up to this you all of you clear, right? Please, please, please respond if you have any doubt up to this. Yes, guys. If you not, then try to answer this question. Come on. Here, two emitter are connected in parallel. So find out the maximum current that we can measure with this combination. Okay, the concept is same. You are not allow the maximum flow of current up to that specify rating, right? For this meter, uh, uh, you are going to measure up to 10 ampere, right? For this meter you are measuring up to 1 ampere. So for that you need to find out the what is a uh, uh, maximum or you can say what is a full scale deflection current for this meter 1. Okay, ifsd IFSD, full scale deflection current for meter 1, and what is a full scale deflection current for this, full scale deflection current for this meter 2. So you can't allow that meter to can't allow that meter excess of this current flowing. Now in this parallel combination the voltage are your reference point, right? So first of all, find out the first of all find out the uh, voltages, right? voltages maximum according to your maximum value of full scale deflection current. Okay, once you find out the voltages, now then only you are commenting what is a maximum value of that current can be passed from this circuit. Okay, because in parallel combination both voltage are same. Okay, if both voltages are same, then IFSD are different for these two because the rating are different for these two meters. Now find out, and try to answer it. Yes guys, please find out what is given to you. There are two meters, that is 0 to 1 meter and 0 to 10 ampere meter. So if I talk about, see, I solve this for 0 to 1 ampere. Okay, so you can solve this for this 0 to 10 ampere meter as well. So for 0 to 1 meter, for meter 0 to 1 ampere. Wait, wait guys, wait a minute. Okay, now for meter 0 to 1 ampere, for 0 to 1 ampere, uh, what is a, this is a meter 2, right? So I consider I2 m or Im2. It depends on you. Okay, so I consider I2m, which is nothing but is a maximum value of current is 1 ampere here. Okay, and we need to find out the voltages, because once you find out the this voltage for this circuit, and that will be same for this circuit as well, right? And this 0 to 1 ampere means this meter reading is small. Okay, so let's see what happened. So I consider here I2 is equal to 1 ampere, right? I2 is, I consider 1 ampere. Now what is a I2 value is V2 by V by R, right? V by R. Now what is the value of uh, wait a minute guys, wait a minute guys, huh? Yes. Now, if I consider maximum current flowing from this meter, so what is a maximum current can be flow from this meter is 1 ampere only. If 1 ampere flow from this meter, what is the voltage drop from this branch is, if I consider maximum current can flow from this meter, that is 1 ampere. If 1 ampere current flowing from this branch, so what is the voltage drop for this is 1 into 100, that is 100 volt, right? So I2, if I consider 100 volt, if I consider case 1, okay, case 1, if I consider I2 is equal to, sorry, if I consider V is equal to 100 volt, V is equal to 100 volt. Now if I consider V is equal to 100 volt, then what is the value of I2 is 100 by 100, because resistance is also 100 and we are considering 100, right? V by R, which is 1 ampere. So meter, our meter will be safe, right? And if I consider same 100 volt for this meter, so what is the value of I1? What is the value of I1? I1 is 100 by, what is the value of this? Our resistance is 25, 25, which is 4 ampere. So for this 100 volt, 4 ampere is flowing from this meter. So that also within your specify range, right? So then also your meter is safe. So both meter are safe. If I consider this V is equal to 100 volt, both meter are safe, right? So you can consider this. If I consider this maximum current, that is 10 ampere, if I consider case 2, if I consider voltage, if I consider this 10 ampere, so what is the drop here? 250 volt, right? So for case 2, if I consider 250 volt, so what is the value of I1? I1 is nothing but your 250 divided by 25, that is maximum full scale reading, right? 10 ampere. So the your meter 1 is safe, right? But when I consider the second meter, so I2 current is nothing but your V by R, which is 250 divided by, what is the value of R here, is 100 volt, that is 100, which is 2.5 ampere. Now see, the range of meter is only for 0 to 1 ampere, but you are getting 2.5 ampere, so your meter will be damaged when you select this range. Okay, meter will damage. So I can say that for this 250 volt, meter 2 will be damaged, will be damaged. Okay, so we are not using this scale. So what is a maximum maximum permissible current flowing from this branch is 1 ampere, up to 1 ampere. For that, what is a voltage drop is 100 volt, right? So we are only use this 100 volt as a safe operating condition. V is equal to 100 volt. Okay, V is equal to 100 volt. Now for this 100 volt, what is the current you can measure from this emitter is 4 ampere. You are already find out this, right? Which is 4 ampere. Now apply the KVL, apply the KCL here, Kirchhoff current law. This is for 100 volt, this is your 1 ampere, and this is your 4 ampere, right? So what is the value of this Imax is 1 plus 4, which is nothing but your 5 ampere, right? So Imax is nothing but your 1 plus 4, which is equal to 5 ampere. Okay, I hope this all of this you're very clear, right? इसमें किसी को कोई भी confusion है तो अभी पूछ लो. Yes guys, means your aim is that you need to save record your readings, right? But your meter should not be damaged नहीं होना चाहिए. Okay, so for that, what provision you need to take, you are deciding with this a couple of by using this a couple of examples. Okay, so that is the two example which I taken here. Practice more. Now, some more terminology is I consider here. You simple read out the definitions. So resolution क्या होता है? If the number of calibration मैंने आपको last time बताया था, okay? So the number of scale is mentioned on your meter, okay? So what is total full scale reading? Total full scale reading. It is a ratio of total full scale deflection divided by number of divisions. So what is a full scale deflection here is 10 ampere. What is a division? 1, 2, 1, 2, right? So two division are there. जीरो को छोड़ दो, जीरो के बाद देखो, एक को छोड़ना पड़ेगा टोटल, अगर इससे काउंट करोगे. सो इसके बाद क्या है, 1 आ गया, फिर 2 आ गया, टोटल 2 रीडिंग्स है इसमें. सो फुल स्केल डिवाइड बाय 2, 10/2 इज 5 एम्पियर। सो इसके बाद जीरो के बाद जो पहला आपका रेटिंग आएगा वो 5 एम्पियर आएगा, सेकेंड इज 10, मीन्स ओके, दैट इज द रिजोल्यूशन। नाउ yes, so these are all these the types of error. So hysteresis error होता है if the meter gives the less than the actual value for the ascending value and shows more than the actual value for the descending value. If the meter gives two different reading for the same input, then it is called as the error. Now एक रीडिंग आप मेजर कर रहे हो, कोई आप शुरुआत से जा रहे थे राइट। फॉर एग्जांपल आप किसी कोई भी डिवाइस का पोर्ट इंक्रीज कर रहे हो, तो शुरुआत में जब आप जीरो से पोर्ट को जैसे जैसे आप क्लॉकवाइज या एंटी क्लॉकवाइज रोटेट करते हो, सो व्हाट इज़ अ वैल्यू, व्हाट इज़ अ रीडिंग is shown on your meter when you reverse that rotation of your port, then at ascending side it gives the some different reading, and in descending side when you reverse the rotation of that port, you will found on your meter a different reading. So that's error is called as a hysteresis error. Also simple verify the hysteresis loop. When you verify this hysteresis loop, okay, something like that, right? So for the same input, now see, for the same input, if I this is your input, right, input and output. For the same input, if I consider this input, right, this is a single input. When you goes this side, you will get this reading, right, this is your ascending. When you reverse back, you will find out this reading, okay. So when you reverse back, you will find out something different reading. So that's error is called as your hysteresis error, okay. I hope this point is clear to you. So this all terminology you are know, please keep you in mind, right, पता रहना चाहिए आपको ये सब. Now the threshold value, if the input of the instrument is increased gradually from zero value, then the minimum value is required on the input to get the detectable change in output. This is called your threshold. So if the any instrument, if you are providing the input, then the gradually increase the from zero value, at the minimum value is required to change your input to get the detectable change in your output. आप जितना भी इनपुट दे रहे हो, ठीक है, जब तक आपको आउटपुट नहीं मिलता है, तब तक जो कंडीशन आती है, सो वहाँ से आप बोल सकते हो कि आपका जो थ्रेशोल्ड चालू होता है, ठीक है। ये दिखाऊंगा मैं आपको बाद में, ओके। देन डेड टाइम इज ऑल्सो दिस, सी दिस ग्राफ, this is your dead time. You are providing the input at different location. These are the different instrument is given to you. For this instrument you immediate get the response, but for this a instrument you providing the input but you can't get the your output. So at the minimum value at which you are getting the response, so the distance from initial to up to that point is called as your dead zone, okay. See here, this is your dead zone for this a meter, and this is for your c meter, b meter, okay, b meter. If I talk about which instrument is best instrument from these characteristics is, tell me which instrument is best instrument by observing these characteristics. So this C instrument is a best instrument. Why this is a best instrument? Now see, because of the linearity. This C instrument has a linearity, linear instrument. So linear instrument is the best one among any non-linear instrument. Okay. Now now you want to find out in this question, now you want to find out the resolution of meter. Resolution of meter हमने पहले अभी ही देखा था ऊपर में, राइट। वो क्या होता है रिजोल्यूशन? रिजोल्यूशन होता है फुल स्केल रीडिंग डिवाइड बाय नंबर ऑफ स्केल। फुल स्केल रीडिंग कितने आपका 10 है, नंबर ऑफ स्केल कितने हैं 100 डिवीजन, ओके, डिवीजन आपका 100 है, बट आपको यहाँ पे निकालना क्या है, you can estimate the one tenth of the scale division. So simple one tenth of the scale division आपको निकालना है, सो मल्टीप्लाई करो इससे. ओके, सो रिजोल्यूशन आपको यहाँ से निकल आ जाएगा. कितना आता है? दिस 10 एंड दिस 10 कैंसल आउट, 0.01. This is your scale of your meter. Okay, and what is a unit of this resolution is volt per division. याद रखना, resolution of your scale is 0.01 volt per division. Now this is a drift. So these are the conclusion, you can read it out. Our time is almost over. Okay, so these are the conclusion, a very important conclusion I am mentioning here. Okay, so whatever we see till now, that I concluded here, you just go through that. Okay, and one more thing, this your pointer is made up with, in next chapter we will discuss the instrument, right? That is we will going to see the brief uh, uh, structure of your any instrument. So in that we will also discuss the what are the damping, which are damping are used in different types of instrument, just like PMMC instrument, MI instrument. So in that, one common thing is that a pointer is there. So pointer is made with aluminum, which are light in weight. So when the force is applied to start the moving very fast, when you apply the force, it start moving very fast. So so the reading which we want, the if the pointer is move very fast, it is very difficult to settle down. For settling that pointer, this vibration of that pointer to settle down, it takes a very last time. So to reduce that time, we are using the damping in any meter. So there are three different types of damping are provided. Okay, so one is over damping, second is critical damping, third is under damping. So the condition are this zeta, this damping zeta. So this is called zeta, and if zeta is equal to 1, it is called as a critical damp. If zeta is less than of 1, is called as a under damp, and if zeta is greater than of 1, is called as a over damp. You already learned this concept with your network and your control system. I think network is over, right, in third semester. So by this, by observing this zeta, you can comment which damping you are used there. Okay, so these are the description is given here. So you please just read it out. Okay, actually we always prefer in measurement, we always prefer actually in measurement, critical damping is a best damping, right? But we are not going to the critical damping. Why? Because the because of aging effect, after after some time, uh, after some time period, your critical damping is going decreases, right? The quality of your instrument get decreases, and your critical damping is converted to the over damping, which is not acceptable, right? So that's why we also not preferable this under damping, because its settling time is quite very means its settling time is also is more. So we always prefer slightly greater than the slightly greater than of your critical damping, but small slightly less than of your under damping. Therefore only for one two oscillation are there, right? All description are given here, just read it out. So that is the best possible damping which we are using in your measuring instrument. And if the option, if objective type of question is framed and such types of option is not given there, then use ऑलवेज अंडर डैम्पिंग। ओके, अगर उसमें ऐसा कुछ डैम्प ऑप्शन नहीं दिखा कि स्लाइटली ग्रेटर देन क्रिटिकल डैम्पिंग बस स्लाइटली लेस देन ऑफ योर अंडर डैम्पिंग, then always use the critical this under damping only। Okay, yes guys, is there any question or you have any doubt with this slide or previous slide? Then please ask. And this week is quite very busy. Last week also, NBA committee will came in this week, and there are lots of pending work are there. Uh, so I, I'm not sure in next class I will be free or not. Okay, yes guys, किसी को कुछ पूछना है तो पूछ सकते हो। If you have any doubt, if you don't have any doubt, so you can leave now। Yes guys,